Good morning, everyone, and welcome to the June 20th monthly presentation of the Institute for Historical Study, which today will be presented by Jim Gasperini on the topic, What is Fire? I would like to remind people we have one of these every month on the second Saturday of the month at this hour. And I believe I have all of the presentations set for this year, but next year is quite open. So anyone who would like to do a monthly presentation, please just contact the board or the Institute generally. Jim is going to talk about fire, which is something philosophers, alchemists, and scientists have been asking, what is it? And he's going to try to come up with an answer that satisfies all of the above. Jim has been exploring this for a long time, and he is currently working on a book called From the Fire in the Imagination, From the Burning Bush to the Burning Man. So without further ado, Jim, the floor, or whatever it is these days, is yours.
Okay.
Oh, and one other thing, everybody, please mute yourselves so that we don't have any interruptions.
Okay, so today I'd like to trace the long history of attempts to answer an elementary question, play on words very much intended. What is fire? As Dan said, from millennia, natural philosophers, alchemists, and finally scientists closely studied nature and struggled to decipher the mystery of fire. And many concepts that, anyway, what I'm showing here is a shot of a charming shot, I think, of Lavoisier, and so that we'll see that again at towards the very end of the story. But to begin with, I'm going to start just imagining that were centuries ago, and many concepts that seem obvious to primary school students today were not at all obvious to our ancestors. Take the nature of air, for example. We feel its effects when the wind blows, yet we cannot. We constantly breathe it in and breathe it out and know that if we were to stop doing so, we would die. Usually we feel it as a single invisible thing, but at times vaporous waters, smells, and sooty bits of earth float around in it. What is air? A flame leaps up for an instant, then disappears. A drop from a stirring spoon falling on the burner vanishes with a hiss. If we stop putting wood on a fire, soon its flames cease their flickering. Embers glow for a time, then one by one turn gray until all that remains is ash. Where has the fire gone? Where did it come from? If we strike certain rocks against one another, we can create sparks and make fire appear again. Where was it until then? What is fire? Implicit in the question, what is fire, is the larger question, what is matter? One classic answer arose independently in many cultures around the world. It proposes that matter is made up of a small number of elementary substances, one of which is fire. But then, what are these elements? Thinking varied widely about the nature of the elements and how they comprise the material universe. Philosophers pondered such questions as, does matter exist externally, or can it be created and destroyed? Are the substances we perceive real, or the manifestations of underlying forms or principles? Are the elements continuous, or composed of tiny invisible particles? Through centuries of such debate, fire was long assumed to be an element, co-equal with earth, water, air, and sometimes others. So, among the Greek philosophers, Empedocles first articulated the idea that everything in the universe is made of four roots, and that the competitive and competition between these four explains the structure of the world. He named them for four Greek gods, but in context, he clearly meant earth, water, air, and fire. Humans experience the various mixtures formed by their competition as different substances. For example, bone consists of 2 parts earth, 2 parts water, and 4 parts fire, while flesh and blood contain an equal mixture of the four roots. Empedocles was perhaps too close an observer of nature. His famous demise in a volcano inspired the classic Danish doggerel, "Great Empedocles, that ardent soul, leaped into Etna and was roasted whole." And that's a picture of him on the right leaping into Mount Etna. Plato, born just after Empedocles died, called these roots elements, a term that stuck and formed the basis for Western natural philosophy for the next 2,000 years. Similar lists of elements or first principles appeared in the natural philosophies of Persia, India, Tibet, China, Japan, and North America, sometimes paralleling the Greeks, but with significant variations. In some traditions, the elements get created in a specific sequence. In Zoroastrian cosmogony, for example, the supreme god Ahura Mazda created the universe in 7 stages. He first created sky, or air, then water, earth, plants, animals, and human beings. All 6 lay inert until the 7th creation, fire, which serves as the life force animating the world. Japanese tradition specifies a list of 5 great elements: earth, water, fire, wind, and void, or sky. In that sense, they're similar to many other East Asian cultures. Sometimes consciousness gets added as a 2nd material element. Could everybody mute, please? Ka, fire, is the main constituent of energetic, moving, forceful parts of the world, including animals and things that destroy. The 5 tapering layers of stone lanterns in Japanese temples and Zen gardens represent the 5 great elements. In the middle, since this is a lantern, of course, sits the fire layer, supported by a bottom layer for earth, then one for water, which is sometimes represented by a lotus flower, and above the central fire layer, layers representing wind and sky gesture upward. Buddhist conceptions of the 4, sometimes 5, great elements also exhibit great variety. Over the centuries, Buddhist philosophers wrestled with complex ideas about the material world we experience through our senses. Is what we perceive real, or the surface reflection of deeper great essentials, or the completely illusory product of our minds? In early Buddhist texts, earth, water, air, and fire were said to be our sensory experiences of more abstract underlying principles: solidity, fluidity, mobility, and heat. Fire consists mostly of heat, though, like every perceptible phenomena, it came to contain a mixture of the 4 principles. Matter is only our mental interpretation of what we can perceive of the true elements through our senses. The colors of Tibetan prayer flags symbolize the 5 elements as we perceive them: yellow for earth, green for water, red for fire, white for air, and blue for sky. Some cultures link the elements with various other phenomena that can be grouped into short lists, such as the seasons, the cardinal directions, and the planets. In one such complex system of correspondences, the Chinese Wu Xing, short for the 5 types of qi dominating at different times, elements consist of cycling phases in continual transition. Each phase gets generated by another phase. Fire reduces wood to ashes, which become earth, from which we derive metal. Metal accumulates water, which nourishes wood, which provides fuel for fire, completing the cycle. At the same time, each phase controls or overcomes another. Fire controls metal, since only with fire can metal be melted and forged. Water controls fire, since it can put fire out. No phase is stronger than any other, since each has its place and function in the eternal chain of life. The one classical Greek element missing from this system of mutual relationships, air, is sometimes identified as the primal qi, the life force underlying all. The 5 phases pervade many phenomena in traditional Chinese thinking. Each phase corresponds with a planet. The one for fire is Mars. Fire also associates with the direction south, the color red, the summer season, the heart among the parts of the body, and the vermilion bird, one of the constellations with symbolic significance, also known as the four auspicious beasts. It has a positive or active yang aspect manifested in wildfires or volcanic eruptions, and a negative or passive yin aspect, which can be brought to serve our needs in the light of a lamp or the warmth of a hearth. The difference, however, between the yin and yang aspects of fire is not great. A campfire, for example, can easily get out of control and burn down the forest. Since some North American indigenous peoples associate the four elements with the cardinal directions, north, east, south, and west, and other phenomena, including stages in life, birth, youth, adult, death, the seasons of the year, and directional winds. In ceremonies, the activating spirits of the elements and directions may be addressed with the respect that is due to living beings and honored for their place in sustaining life. Similarly, many modern pagans also honor the elements along with the directions in their rituals, considering them animate beings. A Manual for Witches by Anne Mura details ceremonies for the full moon, dedications, and important dates in the Wiccan calendar. A ceremony usually begins with casting the circle, laying out a circle with rope or drawing one in the dirt, then placing candles at the four directions. The practitioner lights each of these candles with an altar candle and addresses the direction personally. For the southern candle, Mora says, "I call upon light and fire at the south to illuminate and warm the circle." Later in the ceremony, she raises her wand and says, "I call upon you, elemental fire, to attend this rite and guard this circle, for as I consume life to live, we are kith and kin." At the end, the practitioner snuffs the candle of each elemental power and invites it to depart in peace with her blessings. Mura explains her understanding of the elements as follows. The four elementals are more than the personification of earth, air, fire, and water, more than the symbols of colors, directions, seasons, and aspects. They are real entities of powers that the practitioner can invoke for assistance. There are those who see the elementals as unknowable forces without personality, as a what. My view is that since I am made up of parts of them and I am a who, so are they. I call them my kith and kin. Earth is my body, air moves my breath and stirs my intellect, fire is the spark of energy within me and my passion, and water is my bodily liquids and my emotions. Some of the earliest Greek philosophers also thought of fire as a fundamental force. For Heraclitus, everything is fire. This world was not made by any god or man. It always was and will be an ever-living fire, parts of it kindling while other parts go out. Heraclitus compared the role of fire in the universe with the role of money in the marketplace. All things are exchanged for fire, and fire for all things, even as wares for gold, and gold for wares. Philosophers of the Stoic school, which flourished from the 3rd century BCE to the 3rd century of the Christian era, held a similar view, except that for them, designing fire, quote unquote, creates and destroys all things with purposeful intelligence. Nature is an artistically working fire, a fiery, creative, or fashioning breath. Greek philosophers came up with several other theories about the fundamental building blocks of the universe. The atomists, beginning with Democritus and Leucippus in the 5th century BCE, reasoned that if you cut a piece of matter in half, you still have the same kind of matter. If you cut it in half again and do this over and over, you still have the same matter. There must come a point, however, where you can't divide something anymore and have reached the smallest possible piece of it. They called these hypothetical tiny particles atoms, which literally means uncuttables. Opinions varied about the nature of atoms and their relationship with the elements. Two principles underlie the world, said the early atomists: atoms and void. Tiny, immutable atoms come in an infinite variety of shapes and sizes. They wander through surrounding void until they collide with others and clump together. Their surfaces have tiny barbs and hooks like Velcro, which is how they clump together. We experience these entangled atoms clustered together in many positions and arrangements as material substances. Opinions varied on such questions as to whether atoms are infinitely small or have of finite dimensions, whether the four elements are each made from a different kind of atom or from the same universal substance, whether or not atoms can change from one element to another, and whether atoms are hollow or solid. The idea that the world could be made of very tiny particles recurs in the natural philosophies of many traditions, including the Vaisheshika school of Hinduism and the Theravada vehicle of Buddhism. One Buddhist text I think is wonderfully poetic specifies that an atom, a Puramanu in Sanskrit, is the size of 1/4096th part of a minute particle of dust seen dancing in the sunbeam. Plato argued for a type of atomism based in mathematics, specifically geometry. Everything we perceive, he thought, was made of tiny geometric shapes, comprised of even tinier triangles. Each of the four elements has a different shape. The earth element shape is a cube, made of isosceles triangles, two sides the same length. The other three elements are made of equilateral triangles. Fire shapes have four, making them tetrahedrons. Air shapes are 8, octahedrons, and water shapes 20, icosahedrons. These shapes continually jostle and mix, aggregating into compounds that we perceive as continuous flows of air and water, clumps of earth, and flames of fire. When fire, air, and water shapes collide, their component triangles can break loose and rearranged into shapes of a different element. Earth shapes, made of a different kind of triangle, do not participate in these transformations. The small pyramidal fire shapes have sharp edges and points that can cut into clumps of other shapes, splitting them apart. We perceive this action of mass fire shapes as burning. When external fire shapes come near us, we feel the sharpness of their triangular edges as heat. In Plato's theory of digestion, the sharp edges of fire atoms enable them to penetrate and break up the larger earth and water atoms that make up food. The new fire atoms of young people have sharp triangles that easily slice into reasonable pieces the older and feeble triangles making up atoms of food and drink. Alas, as people grow older, the triangles of their internal fire atoms become blunted with long use, dulling their ability to penetrate and cut. They can no longer easily break up particles of food. Eventually, they degrade to the point where incoming food atoms break them up instead. The body becomes enfeebled and wastes away. This condition is termed old age, said Plato. Finally, when the triangles comprising the marrow snap asunder with the stress, the bonds loosen that attach the soul to the body, and she flies away with gladness. Plato's pupil Aristotle rejected the idea of atoms, asking such questions as, how do we know that these invisible things really exist? What are they made of? Why should a process of cutting things into smaller and smaller pieces stop at a particular point? He denied the possibility of voids, arguing that the existence of a void would mean that what is not exists, an absurdity. Nature abhors a vacuum, he wrote. But if there is no space between particles and matter, counter the atomists, how do they move and rearrange, as they obviously must? Aristotle proposed that the four terrestrial elements are continuous compounds of basic sensory qualities: hot, cold, wet, and dry. Fire is mostly hot, but also dry. Its opposite, water, is cold and moist. Elements can transform into other elements. For example, the sun's rays convert cold, moist water into hot, moist air. In similar fashion, cold, dry earth can transform into the smoky exhalations of hot, dry fire. Flames of lightning display these hot, smoky exhalations at the boil. Though the fiery exhalations naturally tend to rise and join the ring of fires surrounding the world above the atmosphere, they can also get swept up into powerful winds that flow like rivers through the air, slamming into the earth and causing earthquakes. Despite the prominent influence of Aristotle's thinking in both the ancient and medieval worlds, some schools of philosophy continued to promote versions of atomism, notably the Epicureans. The Roman Epicurean Lucretius, 1st century BCE, described minuscule, indestructible atoms moving constantly at enormous speed, bouncing off each other. Despite their rapid motion, they are all so small that we see groups of them at the macroscopic level as motionless or moving slowly. He rejected the limitations of the four-element system, proposing instead a variety of atomic shapes. The different properties of perceptible macroscopic substances are determined by properties of their component atoms. For example, things that feel smooth are made up of atoms that are round, like poppy seeds, while briny things mix smooth atoms with rougher oblong ones. Fire items come fanged with teeth that prick the senses of the body. Until a piece of wood kindles, fire atoms lie interspersed among other atoms like seeds of potential fire. Visible fire consists of fierce streams of fire atoms briefly seen dancing together as tongues of flame. Unable to unite into something fixed, they quickly disperse into the chaotic air. Lucretius objected or rejected the idea that an actual fire element lurked in the wood. If that was the case, wouldn't the chopping action of an axe set it free? He still held to the notion, however, that when something burns, a fire principle or particle escapes into the air. But fire as a potentiality in an unkindled log, rather than the actual fire element, came closer than anyone would come until the
Excuse
late
me.
18th
Everybody,
century.
please, excuse me, Jim. Everyone, please mute your yourselves except for Jim. Somebody's coughing and it's interfering.
I think, Dan, you could also mute people. So, let's see.
I'd rather be volunteer.
Yeah, well, rather than in the actual fire element, Lucretius came closer than anyone would come until the late 18th century to the modern conception of combustion. The debate over the nature and existence of atoms fell quiet early in the Common Era. The idea would smolder, nearly forgotten, for over 1,000 years, then flare up again with the revival of interest in Greek thought during the Renaissance. And Lucretius's book on the nature of things, there was only one copy that survived in a German monastery, and its republication had a lot to do with the rebirth of Greek ideas in the Renaissance. Atomists, of course, had no monopoly on ideas about the nature of fire and the other elements. Speculation about the constituent components of the world continued throughout the primacy of alchemy and into the scientific era. Alchemy, a branch of natural philosophy also practiced in India, China, and the Muslim world, in its Western form began in Egypt in the early centuries of the Common Era, though detractors later characterized alchemists as secretive mystics solely obsessed with changing base substances into gold. They pioneered many innovations in laboratory techniques, metallurgy, medicine, and chemical analysis, setting the stage for the scientific revolution. In fact, some of the most important early scientists were alchemists, including Isaac Newton, the astronomer Tycho Brahe, and Robert Boyle was credited with being the first modern chemist. The insistence of modern science on rigorous experimentation and quantitative experimentation and skepticism of ancient mystical wisdom caused a break with alchemy in the early 18th century. Alchemy went into steep decline, and so it never entirely went away, and particularly popular in New Age circles. The three primes of alchemy, oh my gosh, please. Looking beyond the surface attributes of fire, alchemists saw a principle of combustibility, which they identified with a philosophical version of sulfur. In the mercury-sulfur theory of metals, attributed to influential 9th century alchemist Zabir ibn Ihyan, known in the West as Jiber, the world was primarily made of philosophical mercury, so named because mercury, or quicksilver, is the closest approximation to the underlying principle of volatility. Interacting with this philosophical mercury is philosophical sulfur, also named for a visible substance long known to the ancients. Sulfur, or brimstone, had long been associated with fire due to its yellow color, easy flammability, and the sulfurous odor that sometimes accompanies lightning. Sulfur and mercury are both elements, of course, by the modern use of the term, but just two among many. But how could principles of volatility and combustibility form anything solid, visible, or persistent? The influential Swiss alchemist Paracelsus addressed this problem by adding a third primary element, salt, which he thought to be the closest earthly approximation of the principle fixity. Thus idealized, mercury, sulfur, and salt became the new primary elements. The old Aristotelian four of earth, air, water, and fire were considered subordinates, derived from the new tria prima, the three primes. When a log burns, according to Paracelsus, the salt in it becomes ashes, its mercury evaporates, and its sulfur gets consumed in the flames. Aristotelians used the same example of a burning green wood as evidence instead for the traditional four elements. Robert Boyle summarized their position in the Skeptical Chemist of 1661. Fire is evident in the flame. The vanishing of smoke into air, quote, manifests to what element it belongs and gladly returns. The boiling and hissing on the ends of a green log betrays the presence of water, and the weight and dryness of the ashes put it past doubt that they belong to the element of earth. Throughout the 17th century, alchemists and Aristotelians carried on a lively and sometimes acrimonious debate. Some tried to reconcile the three alchemical elements with the Aristotelian four. After a time, earth regained its status as a primary element, then water. In 1584, the English Paracelsian Thomas Moffat complained about the multiplicity of systems. Some wish that there should be but one element, while others think that there are many, and some even think that there are infinite, innumerable, and immovable. These assert that there are two, those three, some others say four, while others still demand 8. Throughout, let's see, it seemed possible for a time to prove the existence of a fire element by distilling it from an unlikely source. So claimed the German alchemist Hennig Brandt, who spent the fortunes of 2 wealthy wives on a search for the elusive philosopher's stone that could unlock the secrets of immortality and turn other metals into silver and gold. In a 1669 experiment, he distilled prodigious amounts of urine. At the end of the process, a mysterious liquid dribbled out of his apparatus. It seemed to gleam with vital force and spontaneously burst into flame unless cooled. Concluding that he had distilled the element fire, he sold the recipe to a chemist named Kraft, who demonstrated the marvelous self-igniting substance all over Europe. The secret of how to make it leaked out, as it were, and soon early scientists such as Robert Boyle experimented with it as well. Brandt, however, likely brought to public knowledge what was by then a century-old secret alchemical formula. Paracelsus included a recipe for how to distill the element of fire, very similar to Brandt's, in a manual of hermetical medicine. Take urine and thoroughly distill it. Water and earth and air will ascend together, but the fire remains at the bottom. After the fourth distillation, receive the air or the fire in a separate vessel, which put in a cold place, and there will be congealed certain icicles, which are the element of fire. Such distillation can indeed produce not elementary fire, but phosphorus, an element by the modern definition which self-ignites when exposed to air at about 86 degrees Fahrenheit or 30 degrees Celsius. Mysterious conflagrations blamed on witches and demons may have been caused by arsonists who bought fire phosphorus from an unscrupulous alchemist. A century after Brandt's discovery, experiments with burning phosphorus would play an important role in solving the riddle of combustion. So, natural philosophers long noted the special relationship between fire, air, and life. Ideas for how this relationship worked flowed back and forth over the centuries. The Stoics conceived of an active vital force that they called pneuma, a combination of fire and air like a fiery breath. This fiery, creative, designing breath generates all form and motion in the material world, shaping and holding bodies of matter together. It burns on the spiritual level as well, shaping and holding bodies, giving animals their life functions, animating their souls, and enabling reasoning animals to think, plan, and make decisions. Others proposed that the air contains some sort of food for fire. This would explain why a candle placed under an airtight jar will soon go out. Without a fresh source of air, the candle will use up all the aerial fuel. The fire food, pabulum ignis, or haunter in the air, as it was variously called, must be something other than the wax in the wick, since the candle burns normally until placed under the jar. Much like a candle, an animal placed under a jar will cease to breathe and go out. Why? Paracelsus reasoned that since we die if we cease to breathe, a vital life flame, which he called the flamma vitalis, must permeate the air. The Irish philosopher George Berkeley described air as a mass of various particles permeated by animating force of pure invisible fire, the animal spirit of the visible world. Some identified the vital flame with the philosophical element sulfur. Others thought fire to consist of minute sparks struck from collisions between particles of sulfur and niter, potassium nitrate, another substance thought to permeate the air. Paracelsians proposed that both sulfur and niter, the active ingredients of gunpowder, flow from the stars. Some stars exhale sulfur, while others give off niter. When these emanations mix, this gunpowder in the air can explode, producing thunder and lightning. Other proposals envisioned an inverse of this cosmic respiratory system. Fiery exhalations rising from the surface of the earth feed the stars, comets, and sun. The French naturalist Jean-Baptiste Robinet proposed that sunspots result from smoky exhalations attracted to the solar surface. In time, he warned, in De la Nature, 1766, the sun may absorb so much of this material that the light will go out. But as Gaston Bachelard commented dryly, the stomachal rhythm of the universe must be very powerful if the Sun King will die from overeating. Though we have much to concern us about the effects of our own smoky exhalations on the planetary climate, At least we need not worry too much about extinguishing the sun. From ancient times, people knew how to fear something gone bad, suffocating or poisonous vapors often found lurking in confined spaces. The Romans lowered lamps into caves and mines before entering, watching to see if they continued to burn to avoid mysterious suffocating miasmas. Caged canaries served the same purpose later on. Studying these vapors, the Dutch scientist and chemist Jean-Baptiste van Helmont, who lived from 1580 to 1644, isolated a substance emitted when charcoal and alcohol burned. He then found the same substance discharging when beer and wine ferment and when vinegar mixes with the shells of crabs. He called it a gas, from the Greek word chaos. We now call the gas he studied carbon dioxide. Later scientists isolated other invisible gaseous substances, calling them variously factitious airs, modified airs, aerial acids, or elastic fluids. Combining oil of vitriol, sulfuric acid, with iron nails produced flammable air, quote unquote, later known as hydrogen. The combination of aqua fortis, nitric acid, with oyster shells liberated a fixed air that was not flammable, nitrogen. Were the airs produced by these procedures modifications of the element air, or foreign substances dispersed within it? Or was the atmosphere just a receptacle for airs of different sorts? It took many years of experimentation for properties of the different types of air to be sorted out, appropriate names agreed upon, and theories developed to explain these differences. Van Helmont's coinage gas eventually won out as the general term for airs of different kinds. As early scientists performed experiments trying to explain fire, they were on the right track in suspecting that some segment or constituent of air enables flames to burn and bodies to respire. For some decades, however, attention shifted from the mystery of this vivifying spirits in the air to interpretations of combustion as a mechanical process. People have long looked for keys to the secrets of the universe by studying their own inventions. The Western world was still exploring the uses of the Chinese invention gunpowder when alchemists hypothesized that lightning, flames, and the heat of the body could all be explained by explosive interactions of sulfur and niter. In recent times, the idea that the universe might be a vast computer simulation has had its vogue. During the scientific revolution of the 16th through 18th century, many proposed that the world might be a vast machine. Among the most influential ideas were prompted by the rediscovery of ancient Greek and Roman texts during the Renaissance was the atomist conjecture that the world might be composed of tiny particles. At a time when mechanical devices such as clocks were becoming increasingly sophisticated, the workings of tiny moving cogs in intricate clockwork suggested an analogy with tiny moving bits of nature. Mechanist philosophers speculated that nature might consist of a vastly complicated machine, intricately composed of discrete interacting parts. Some claimed that this watchmaker analogy proved the existence of God, who set the machine in motion and may still be directing its movements. By understanding the way the machine works, they hoped to better understand the mind of the Lord. Others thought that the world could work like a machine without guidance necessarily by a divine hand. Making a methodical study of the various sources of heat, the English natural philosopher and statesman Francis Boyle, 1561 to 1626, determined that their common element is rapid motion, as exemplified by the constant flickering of flames and the roiling of hot liquids. He reasoned that heat is not a property inherent in a fire element or driven by a vital spirit, but produced by the movement of small particles of matter interacting mechanically. Galileo Galilei took a similar position. Those materials which produce heat in us and make us feel warmth, which are known by the general name of fire, would then be a multitude of minute particles having certain shapes and moving with certain velocities. Meeting with our bodies, they penetrate by means of their extreme subtlety, and their touch, as felt by us when they pass through our substance, is the sensation we call heat. Bacon and Galileo both figured prominently in the development of the scientific method. Bacon went beyond the ancient practice of close observation of nature by systematically comparing different sources of heat and light, analyzing what they had in common, what they did not, and using inductive reasoning to explain his empirical observations. But to fully answer the difficult question, what is fire, required the development of more advanced techniques of experimentation. The invention of more sophisticated equipment, typified by Galileo's experiments with the telescope, spurred these more sophisticated techniques. The increased refinement of tools and techniques did not, of course, guarantee accurate interpretation of the data produced. Robinet, for example, believed that fire consists of igneous beings that grow from germs like plants and animals, have natural lifespans, grow old and sterile, and then in time die even if well fed. After striking a flint over a sheet of paper, he observed through a microscope, which he was delighted to learn how to use, and he observed charred specks and some round and shiny atoms, although the naked eye could see nothing. They were little shiny worms of fire. So, though natural philosophers sometimes drifted in circles around the problem of fire, discarding certain ideas only to revive them decades or centuries later, they gradually spiraled closer to a solution. Along the way, they sometimes spun off into strange side currents. The eminent French philosopher René Descartes took a purely mechanistic view of the universe, rejecting ideas of animate or divine direction expressed through a vital force. He also rejected the atomist notion of voids between particles. He and his followers recognized only three elementary substances: fire, air, and earth. They considered water secondary. All three, they thought, are composed of corpuscles, particles similar to atoms but capable of further division into smaller parts. Whenever a corpuscle moves, another slides into its place from behind. Meanwhile, a third slides in behind the second, and so on. Strings of corpuscles tend to move in circular patterns, forming vortexes. These circular patterns of movement occur on many levels. A pattern of immense vortexes explains or vortices, explains the circular movement of the planets. The Cartesians Nicolas Malebranche specified that the subtle or ethereal matter is composed of an infinity of small whirlpools that turn on their balance. When the equilibrium breaks, the phenomenon of combustion, of lightning, or the bursting of gunpowders occur. According to the Cartesians, fire corpuscles, the smallest and most fluid of the elements, can change shape and size and break apart to fill any pores or crevices that might threaten to open between clusters of larger corpuscles. The rapid movement of fire corpuscles creates heat. Merely by rubbing our hands together, we heat them, Descartes observed, and any other body that can also be heated without being placed close to a fire, provided only that it is shaken and rubbed in such a way that many of its small parts are moved. Contrary to Aristotle, he thought that fire particles do not naturally rise to the sphere of fire around the globe, but move in every direction, which can be directly seen in the flickering of a flame. They tend to move upward only because they follow the path of least resistance, pushed by the pressure of larger and more stable particles. The influential Dutch chemist and physician Herman Boerhaave, who lived from 1668 to 1738, thought of fire as omnipresent, elusive, but pervasive, subtle matter, quote unquote. Minute fire particles exist everywhere. penetrating the pores and interstices of even the most solid gold as well as the most empty vacuum of an air pump. Instead of the deformable and breakable corpuscles of Descartes, his fire atoms are corporeal, solid, spherical, and immutable in size and shape. They are not, however, subject to gravity. Fire atoms repel each other and try to expand, providing the impetus for action and movement in the world. This pure fire serves as God's instrument for effective impetus for action. For affecting motion and change, pushing and forming other elements into their shapes and configurations. It gives air its elasticity. When ignited by friction, the parallel rays of the sun or a spark of quote-unquote vulgar fire, fire particles can break the bonds of attraction that keep clusters of earth atoms together. The clusters burst apart, and the fire atoms shoot forth as the heat and light of flame. Though Boerhaave's was a mechanical vision like that of Cartesians, his conception of solid atoms attracting and repelling each other drew from the increasingly influential theory of invisible forces central to the thought of his English contemporary Isaac Newton. Against the objection of the Cartesians, who considered the concept of forces acting between distant objects a preposterous revival of ancient animist ideas, Newton's principle of gravitational attraction steadily gained precedence as their superior explanatory power became apparent. Leading scientists long persisted in the mistaken conviction that the energetic action of fire consists of flammable substances and rapidly spinning apart. This is what combustion looks like, after all. When a log burns, it dismembers. We can see with our eyes, wrote Descartes, that when flame burns wood, it moves the small parts of the wood that separates them from one another. The disruptive power of fire alone will be able to cause in the wood all the same changes that one experiences when it burns. It took centuries for a counterintuitive idea to take hold. Combustion actually consists of things combining in chemical reactions. A step towards understanding the importance of chemical combination came from the German alchemist and physician Johann Joachim Becher. In 1667, he imagined the existence of a sulfurous or oily principle mixed into various substances in different proportions, which his student George Stahl named phlogiston, from the Greek phlogistos, burnt or inflammable. Phlogiston, they thought, can be found mixed into all flammable substances. When something burns, the phlogiston particles it contains vaporize. When its phlogiston finishes burning off, combustion stops. Vaporized phlogiston spreads through the air until absorbed by plants, then gets passed into animals and minerals, and the cycle returns again. Though much of phlogistic theory amounted to old sulfurous wine in a new bell jar, it plausibly fit the new known data, offered a useful solution to a complex problem, and dominated chemistry for decades. In the second half of the 18th century, however, researchers performed experiments that called into question its very existence. In the 1770s, the pace of scientific advancement picked up as a small group of competing researchers in several European countries addressed the problem of explaining fire. As chemists and natural philosophers, the term scientist did not come to use until the 1830s, came closer to solving the enigma of fire, intense rivalries underlaid the collegial correspondence and sharing of results between members of the Royal Society of London for Improving Natural Knowledge and the Paris Académie des Sciences. Though many researchers contributed to the exciting developments, the principal figures were the English chemist, theologian, and political theorist Joseph Priestley and the Swedish pharmacist Carl Wilhelm Scheele, each of whom discovered oxygen independently, and the French chemist Antoine Laurent de Lavoisier, who identified oxygen's role in combustion. Priestley had a noble patron who supported his work, though not lavishly, Lavoisier, a nobleman himself, used his powerful position in the French aristocracy to provide himself with the finest laboratory equipment available. When Scheele wasn't running a pharmacy business in the small town of Köping, Sweden, he was able to borrow a friend's modest laboratory in nearby Uppsala. All three assumed phlogistic chemistry to begin with. Crucial advances in the scientific understanding of fire came from the study of a special form of combustion, the calcination of minerals and metals. Certain metals will, when heated to the point of burning, transform into a crumbly powder known at the time as a calx, now known as an oxide. Mysteriously, when metals become calxes, they get augmented. They weigh more after burning than they did before. But if the process of burning releases fire particles, like the phlogiston theory would have it, from something burned, as had always been assumed, shouldn't what remains weigh less? The process of burning wood was hard to measure with instruments of the time, what with smoke, ash, heat, and vaporized moisture all going in different directions. The simpler calcination of metals offered a way to experiment with more precision. Researchers conducted experiments using inflatable bladders, air compressors, vacuum pumps, piston and valve instruments, glass and copper tubes and globes, swan-necked glass retorts, tobacco pipes, bell jars, pneumatic troughs, pneumatic shelves, bottles partly filled with water or mercury, receiving vessels suspended from wires, gas cylinders, glass lenses, precision scales, and ox bladders. They executed tests using iron wire, lead, copper, brass, tin, phosphorus, manganese, mercury, the calxes of all these metals, pyrite, saltpeter, silver carbonate, various nitrate salts, and many types of acid. For heat, they tried candle flames, smoldering charcoal, and the rays of the sun focused through a burning glass. Living near a brewery in Leeds, where vats of fermenting barley wort produced great quantities of fixed air, or carbon dioxide, Priestley experimented with impregnating bottled water with it, hoping to invent a cure for scurvy or cancerous ulcers. The bubbly product did not pan out as medicine, but in the process, he invented carbonated water. He could have made a fortune on this discovery, as a Swiss scientist named Schweppes promptly did, but among Priestley's many theological, philosophical, and political pursuits, making money was never a priority. He then isolated other airs, including nitrogen, carbon monoxide, and sulfur dioxide, though his analysis of what he had produced had many flaws. In August 1774, he isolated a surprising new air. Heating the calx of mercury seemed to remove phlogiston from the air and put it back into the metal, leaving the remaining air dephlogisticated. Candles burned brightly in this new air, and animals breathed very freely. Testing it on himself, he found it 5 or 6 times better than common air. Following a reverse process, burning a metal into a calx or a candle in an enclosed space, he observed that the confirmed air killed candles and mice alike. He called this phlogisticated air. Today we call the depleted phlogisticated air nitrogen and the nourishing dephlogisticated air oxygen. A little before Priestley began this work, Scheele determined that phosphorus burned readily in what he called fire air or oxygen, but not at all in vitiated air, nitrogen. He determined that the two airs comprised most of the common atmosphere, measuring their relative proportion with reasonable accuracy. Interpreting these results in the light of phlogistic theory, he proposed that fire air, the elastic minor constituent fluid of the atmosphere, eagerly attracts phlogiston, while the major constituent does not. His conclusions partially anticipated those of Lavoisier, except that Lavoisier, armed with information from Priestley, was soon to abandon phlogiston altogether, and in so doing, revolutionize chemistry. On a visit to Paris in October 1774, Priestley demonstrated his surprising discovery of dephlogisticated air to Lavoisier and other assembled savants. Lavoisier quickly duplicated Priestley's work and recognized the significance of the discovery better than either Priestley or Scheele. A famous experiment in 1777 clinched the question for Lavoisier. It focused again on the calcination of mercury, a metal with unique properties. At a gentle boiling temperature, liquid mercury combines with oxygen to produce a red calx oxide. If this calx then gets heated a little more, the mercury gives off the oxygen again and precipitates back into liquid form. Lavoisier managed to do this back and forth in an enclosed space without using charcoal, which would have been a possible contaminant. He showed that when the mercury turns into a calx, the enclosed air becomes depleted. Then when the calx gets heated more and mercury precipitates out, the air returns to its original state. He had definitively proved that a burning metal combines with a part of atmospheric air to form a calx, and the weight of the air fixed in the calx accounts for its augmentation. The substance that Scheele called fire air and Priestley dephlogisticated air, Lavoisier named oxygen from the Greek term for acid generating. He declared that multiple types of air exist, that they are not modifications of common air, but separate components, and that one of these elastic fluids, oxygen, was salubrious and kept flames and animals alive, while the other, nitrogen, was inert and extinguished them. He broke with phlogistic chemistry, declaring phlogiston to be an imaginary, unnecessary notion. In doing so, he chose an unpopular, counterintuitive theory, performed careful experiments to substantiate his ideas, and promoted this theory relentlessly despite initial opposition. At long last, a plausible, data-driven solution had been found to the ancient question, what is fire? Fire is the rapid oxidation of burnable substances, fuel, in a chemical process that releases heat, light, and other products. Lavoisier's work revolutionized chemistry and laid the groundwork for modern sciences. Phlogiston, the last incarnation of the fire element, which had the accumulated weight of millennia of mistaken thinking behind it, did not go down without a struggle. Advocates, including both Scheele and Priestley, continued to fight a losing battle to explain new data with some role for phlogiston. Their interpretations grew increasingly labored and complex. Phlogiston theory reversed modern understanding, interpreting the gain of oxygen in a burning substance as the loss of its phlogiston. According to one scholar, this inversion was in great part responsible for its successful, if often complex and quaint, interpretations of biphlogistic chemistry. An explanation and its virtual inverse may well be equally successful over some considerable range of data. Eventually, phlogiston became remembered as a peculiar, outmoded idea that somehow hung on long after its days permeating the pores of the universe should have passed. Chemistry advanced rapidly in the decades following Lavoisier's big conceptual leap. Through years of experimentation and debate, researchers sorted out the differences between different flammable gases, including hydrogen, methane, and carbon monoxide. The discovery that water is composed of a flammable air, hydrogen, and vital air, oxygen, brought down another of the Aristotelian four, confirming the revolutionary turn in the science of chemistry and cementing this change as one of the most important conceptual leaps of all time. The principal discoverers of oxygen and its role in combustion became famous in varying degrees. Joseph Priestley led an extraordinarily varied and dramatic life. At one point, his support for the French Revolution and radical Unitarian religious ideas provoked an angry mob to burn down his house, laboratory, and church in Birmingham, England. He escaped to Philadelphia, where he lived into the 19th century, still holding a torch for phlogiston, his preferred theory of fire. 𝘞𝘩𝘢, the least known, also discovered barium, manganese, molybdenum, numerous types of acid, chlorine bleach, and a method for mass-producing phosphorus that sparked the world's leading Swedish match industry. Many of his discoveries were long attributed to others, including that of oxygen. Although 𝘞𝘩𝘢's work had actual precedence, both Priestley and Lavoisier published their results before he did. Alas, he did not live to see much of the fruits of his labors, dying in 1786 at the age of 43 from the cumulative effects of exposure to the many poisonous chemicals used in his experiments. The aristocrat Lavoisier, despite his stature as one of the greatest scientists France ever produced, lost his head to the guillotine on the Place de la Révolution in Paris. He was not, however, just an innocent scientist, unfortunately swept up in revolutionary madness. For Lavoisier, experimenting with fire was something of a gentleman's hobby. His day job was architect and administrator of the oppressive system of taxes under Louis XVI that did much to provoke the revolutionaries. Beginning with John Dalton's work classifying elements by atomic weight in the early 19th century, the empirical methods of modern science confirmed a version of the metaphysical thesis of ancient atomists, that matter comprises minute particles of different types. The ancient terms atom and element, applied to so many wildly different concepts over the centuries, settled into standard scientific definitions. Over 100 elements are now thought to exist, distinguished by how many protons they contain. An atom is an individual instance of an element. Only in the last century have we learned how to split uncuttable atoms apart, unleashing the powerful energies of nuclear fission. It can be argued that Empedocles and the many others who struggled to long squeeze the universe into a short list of 4 or so elements were onto something not that distant from modern scientific understanding. The classical elements earth, water, and air roughly correspond to 3 states of matter: solid, liquid, and gas. Fire is the odd one out in this analogy, unless understood as the energy that transforms one state of matter into another. If hot enough, fire can actually produce a 4th state of matter, plasma. Created by the ionization of superheated gases, atoms stripped of their electrons, plasma can be generated by lightning or an acetylene torch. It also floats inside the tubes of neon lights. While relatively rare on Earth, plasma is by far the most common state of matter in the universe. The stars consist mostly of plasma. While considering the stars, it may be worth digressing briefly from our focus on terrestrial fire to consider the term burning when used in a stellar context. While Earth combustion centers on oxidation, the process of combining other substances with oxygen on a molecular level, the energy of stars comes from fusing lighter items into heavier ones. The sun burns about 600 million tons of hydrogen into 596 million tons of helium every second, releasing energy from the difference in mass. It will go on doing this for the next 5 billion years or so. In stars much more massive than the sun, when all the hydrogen fuel gets turned into helium, the helium atoms start to burn, 3 at a time, fusing into 1 atom of carbon. When all the helium has burned, the carbon burns into oxygen, which in turn burns into neon, followed by a series of burnings into ever heavier elements: magnesium, silicon, sulfur, and finally nickel and iron. Other types of stars of different mass and density also burn elements at different stages of their life cycles, particularly during massive explosions called novas and supernovas. From the deaths of generations of stars come all the heavy elements of which our planet and we ourselves are made. Once science figured out its chemistry, fire lost some of its importance in the imagination. Chemistry downgraded flame to an atomic reaction, says fire historian Stephen Pine. Fire shrank from Heraclitean universality to a laboratory demonstration. Once the manifestations of the deity and the sources of life, fire had become alien, a destroyer of cities, a savager of soil, a befouler of air, an emblem in science and in agriculture of the hopelessly primitive. I think he kind of overstates the case there. As Gaston Bachelard reminds us, a slightly hypnotized fascination remains surprisingly constant in all who watch a fire. Many still prefer the warm glow of a candle or a fireplace to the more efficient and convenient but colder electrically powered luminescence, particularly when in a romantic or convivial mood. We still use fire for fun, lighting celebratory fires on occasions ranging from the solid to the silly, such as summer solstice happening as it happens tomorrow, and to signal serious intent when performing rituals and ceremonies. And although at long last we have begun to move away from it, our civilization still largely relies on burning stuff for our energy needs. Okay, and this is drawn from a chapter of my book, as Dan said at the beginning, and you can find more about that on my website. So now I will stop sharing.
Well, thank you very much, Jim, for that fascinating discussion of fire. As you point out, the summer solstice is tomorrow. I just looked it up while you were talking. And so it's rather appropriate that if we talk about fire on that. I'll open the floor to questions now, and I'll take advantage of my position to ask the first one, which is you talked about alchemy and alchemists, alchemy appearing all over the world. And I wonder if that was independently explored or if there was some influence from the early alchemists to in one part of the world connecting to later alchemists, maybe along the Silk Road, for example.
Very much so. Yeah, I think I mentioned that a influential Muslim alchemist at one point and influenced Western conceptions, and I think it probably mostly went from east to west. But yeah, the alchemists were love to share ideas like that.
Everybody, please unmute yourselves if you want to ask.
Well, I have to leave. I'm sorry.
All right, bye-bye. Whoop, now she's gone.
Bertram.
Yes, hi. I have to leave soon too, but I did have a sort of question comment. It might be interesting as a kind of sidelight direction for your work, which is fascinating talk, by the way, to look up in the Oxford English Dictionary the many definitions of the word fire. You know, I was thinking of somebody gets fired from their job or whatever, and I don't know if you've explored this at all, but we use just in the English language alone, we use the word in so many different, not necessarily contradictory, but so many different ways. I don't know if you had any comments on that, but it'd be, as I said, be easy enough to look at the OED and you get a history of the term fire and its many uses.
Yeah, I do have in a different chapter of the book, I do talk about some of the range, particularly those that have to do with kind of spiritual concerns and mythology. But yeah, you're right. It is and I go into the term agni, which has a lot of how that comes from a Indo-European root, and it went it split from on the eastern side. It became referred to the sort of the dynamic aspects of fire, and it was personified in the Indian god Agni, whereas it became more of a sort of a secular on the western side, and was used to describe things like igneous rocks and ignition. That term has many different roots, one root in many different manifestations.
That'd be interesting. Very good talk. Thank you very much.
Well, you're welcome.
Any other questions, discussions, arguments?
I've left you speechless.
All right, then. Thank you very much, Jim, for that. I'll remind everybody that on the third Saturday of the month, I spoke before, it's not the third Saturday of every month except December, we have one of these monthly presentations. Next month will be Peter Stansky, who will be talking about George Orwell, subject that he knows a great deal about, and which is rather relevant to the current political situation, but I'll let Peter talk about that next month. Thank you all, and especially Jim, and we'll see you on next month.
All right. Bye-bye.